But there are things that you want to, whenever you're challenged with the synthesis problem, things that you want to think about or check on. All right, so first of all, it helps sometimes not just to think about the starting material and trying to get to the product, right, but thinking about the product, how can I make that product in one step? What reactions do I know that can give me a ketone? And try to work back one step. And that's going to shorten the overall synthesis then, in this case, to 2 steps. All right? So far, we don't know many reactions that synthesize ketones. Right? We haven't learned any oxidation reactions. We've learned one reduction reaction that can give us ketones. And then all of the other reactions that you've learned that make ketones come from functional groups that are derived from ketones. Right? Things like ketals. Right? We make a ketal from a ketone. We could make a ketone back from a ketal. All right? So there aren't too many options for making this product. All right? The other thing that you want to do is try to account for your starting material in the product. Right? Because those are the atoms that you don't need to change, and you can also figure out what connections you need to make. Right? So if we look at this starting material, I can say that this 6-membered ring here is going to be the same as that 6-membered ring there. Probably, right? Not 100% sure, but that's what it looks like to me. All right? That also means that this carbonyl here, which we'll just call carbonyl A, is going to be the same carbon as that carbonyl carbon there. Okay, and what this means then is that in order to do this synthesis, right, you need to make a carbon-carbon bond. So the product is telling us eventually what we need to add to that carbonyl. All right, we need to add a carbon nucleophile to the carbonyl because we need to make that carbon-carbon bond. Right, so if you're thinking about adding hydride reagents, adding alcohols, that kind of stuff to make the ketone, right, none of that's going to work, right? Product tells you what type of nucleophile you need to make that ketone. All right, so when we start thinking about this, right, if we need to add a carbon nucleophile, what's the only carbon nucleophile that you know how to use so far? Yeah, the Grignard reagent. Okay, if we add a Grignard reagent to a carboxylic acid, what's going to happen? Can we make carbon-carbon bonds to carboxylic acid using Grignards? No, Grace, why not?
Because the center carbon isn't as electrophilic.
Good, it's not as electrophilic. More importantly, we have an acidic proton, right? So if we add a Grignard to this carboxylic acid, we're just going to deprotonate the carboxylic acid, right? This makes it no longer electrophilic. We don't have a Grignard anymore, so it's just going to be an acid-base reaction, right? So we need to change this carboxylic acid into something where when we add a Grignard, we make a ketone. All right, so what would that be? What other carboxylic acid derivative do you know that can form ketones?
We made it into an acid chloride over here.
Okay, all right, so that's, I think, a good first step. And so how did you do that, Joey?
We added SOCl2 in alcohol.
We're not going to add an alcohol, although that would be interesting. So, yeah, we can talk about that in a second. Yeah, so we'll say that this is done in dichloromethane. Right, we'll get back to your alcohol idea in just 1 second. Okay, and that's going to form an acid chloride. If we were to do this in an alcohol, say ethanol, that would result in the formation of an ester, of an ethyl ester, and which is really the equivalent of forming an acid chloride, right, and then treating that acid chloride with ethanol. Okay, that's really essentially the thing that's happening in here. We're forming the acid chloride, but we have a solvent that's also nucleophilic. So once we form that acid chloride, the solvent's going to react to form the ester. Okay, so we could do either of these actually. Either of these would be a fine first step. Right, forming an acid chloride or forming an ester, right? But again, if we add a Grignard to an ester, right, we're going to get 2 additions of that Grignard, and we're going to make a tertiary alcohol. Same thing with an acid chloride. If we add a Grignard to an acid chloride, we're going to get 2 additions, and we're going to form a tertiary alcohol. So what do we have to do to the acid chloride of the ester next before we make the amide, or before we make the ketone? Yep.
Make it into a wine grape.
Excellent. Right, so the other day we learned about a functional group called a wine-reb amide. We said that the wine-reb amide was the only amide that you could add a Grignard to and make a ketone. Right, so to make the wine-reb amide, we just put in the methoxymethylamine. Okay, add 2 equivalents. Right, because one of them has to act as a base. Okay, that's going to get us to the wine-reb amide. Right, and then we're one step away from the ketone. So remember, when we add Grignards to wine-reb amides, we're adding once. We form this stabilized intermediate, and then when we work up the reaction, that intermediate collapses and gets us to the ketone. Right, so for the Grignard reaction, we would add our Grignard reagent. Ethereal solvent, and then follow that up with an acidic quench. Questions about this?
What's the importance of writing the 2 equivalents?
Yeah, so if we go through this mechanistically, what happens, right, we add the amine, we kick out the nitrogen, and the intermediate that we're forming is an acidic intermediate here, right? When we form this, this is unstable, so a base has to come by and pluck that proton off. Right, so if we have this in the reaction, it's going to act as a base, whether we like it or not, right? And so as a result, because it's going to act as a base, whether we like it or not, we have to put in that second equivalent just to respect the reactivity. And, yeah. Other questions? Okay.
You said the wine grape amide is the only amide you could add a Grignard to or carbon.
No, the only amide you could add a Grignard to and reliably make a ketone. Yeah, so the book says that you could add a Grignard to any amide and that will result in the formation of a ketone. That's not actually true. Wine-reb amides, I mean, that can happen with some amides, but definitely not all amides. And so wine-reb amides are kind of a reliable way of making a ketone. There's no ambiguity there. Make sense? Other questions? Okay. All right, so let's talk about chapter 11 a little more today. So chapter 11 goes over chirality. And I said the other day in class when we started talking about stereochemistry and chirality, I'll give you a couple of examples of the impacts of chirality. So up on the board, there are 3 sets of enantiomers. Okay, we have carbone, ibuprofen, and a molecule called thalidomide. Some of you might have heard of all or some of these molecules. And so we said the other day that 2 enantiomers are going to have all of the same physical properties, right? So R minus carbone, S plus carbone. If we take the NMR of those molecules, the NMR is going to look exactly the same. GCMS is going to look exactly the same. Melting point, boiling point, going to be exactly the same. The way that they interact with plastic is going to be exactly the same, right? So the only difference between these two comes in the way that they rotate plane polarized light, right? One's going to rotate light clockwise, the other is going to rotate light counterclockwise, but to the same degree. And then the way that they interact with other chiral materials, chiral compounds. Okay, So first of all, R carbone, S carbone. So R and S, we're going to learn that today. That's just a way of communicating the stereochemistry or the configuration around a tetrahedral center. Right? Did you all learn R and S last year? No, maybe yes, maybe yeah. Some of you remember. Okay, so we'll go over it again. Okay. The other thing in this name that you can see is that one has a minus and one has a plus. All right. All this means is that this rotates light clockwise. It's a plus, right? And the minus indicates that it rotates light counterclockwise. Okay. R and S, plus and minus, have nothing to do with each other. Right? So you can have a stereo center that is named as an R stereo center, and it will rotate light clockwise. You can have another stereo center of another molecule, right? Like carbone, that rotates light counterclockwise. Sorry. Okay, so R is just R and S are just our way of naming stereo centers and communicating configuration around that stereo center. Plus and minus indicate which way that molecule rotates. Not all names are going to have the plus and minus. All chiral molecules will rotate plane polarized light one way or the other. Okay. So R carbone and S carbone, these are molecules called terpenes. They are flavor compounds. R carbone has the sweet smell of spearmint, where S carbone has kind of an earthy smell of caraway. Right, does anybody know what caraway smells like? What do you smell caraway in typically?
I don't know, it's kind of sweet.
It's kind of sweet, yeah.
Rye bread.
Rye bread, yeah. So marbled rye bread, any rye bread that you would get from a deli, or probably baker has rye bread, right? Just stick your face in the bag of rye bread and take a whiff. What you're smelling is a lot of caraway, right? The seeds on top of rye bread, those are caraway seeds, right? Obviously very different from spearmint. Molecules are just enantiomers of one another, so the difference in smell comes in how they're interacting with our scent proteins, right? Obviously, one of them is able to trigger the smell for spearmint, right, in one protein, and the other is able to trigger the smell for caraway in a different protein, right? So they're interacting with different proteins or interacting with the same protein in a different way because the proteins that they interact with are chiral entities. Right, so kind of interesting. Let's say a more interesting case is ibuprofen. Right, so you've all taken ibuprofen at some point for sore knees, headache, hangover, whatever. There are two enantiomers of ibuprofen. Okay, S-ibuprofen is 26 times more effective as a drug. Right, 26 times more effective at stopping pain. All right. When we buy ibuprofen, both enantiomers are part of that pill. All right, and the reason why both enantiomers are part of that pill is because our ibuprofen doesn't cause any harm. Right, it actually does dull pain, just not very well. Right, it's not very good at binding to that receptor that as S-ibuprofen. And again, that comes with the shape of the molecule due to the chiral center, right? Due to the change in chirality. One can bind to that receptor a lot stronger, right? One can't bind to that receptor as strong. Okay, so we get one enantiomer that's more effective, one enantiomer that's less effective. It would be so expensive to make pure S-ibuprofen, right, that we don't do it. We'd be paying $20 per ibuprofen pill, right, which you might do when you go to the hospital anyway. But nonetheless, because our ibuprofen doesn't cause any harm, right, just put both into the pill, and it's cheap, easy to take. Yeah.
What is the S's and R's for?
Those are just ways of communicating the configuration of the stereo center. We'll talk about that in a little bit. Other questions? Okay, so probably the most famous case of the consequences of wrong stereochemistry in drugs comes from thalidomide. People have heard of thalidomide? It's a pretty infamous story. So structure of the thalidomides up here, you can see that there are two enantiomers, R and the S enantiomer. This is actually still a drug that's in use today, but this drug came about in the 1940s in Europe as a way to treat morning sickness in women who were pregnant during the first term. This drug was one of the first drugs that was not approved by the FDA, right? So the U.S. looked at this drug and said, we don't want it here for morning sickness anyway, right? And it wasn't approved. But it was given to women in Germany and in Great Britain. And what they found is that one of these enantiomers, in fact, is really effective at treating morning sickness, the nausea from morning sickness. But the other enantiomer causes really horrible birth defects, right? So the women the children who were born from women who were taking thalidomide, a lot of them were born with hands coming out of the shoulder, so no arms and no legs, but they had hands and feet, right? Really bad birth defects. A lot of the children were just stillborn, right? So they weren't born at all. And what they found, again, is that one enantiomer treating morning sickness, one enantiomer, right, didn't, and caused those really horrible birth defects. The problem is, even if you make this enantiopure, even if you say, I think it's the S enantiomer that treats morning sickness and the R enantiomer is the mutagen, even if women ingested just this enantiomer, right, the chemistry of the stomach would actually cause this to what's called racemize, right? So it would reform a 50-50 mixture of the two enantiomers, right? So the body would make the bad enantiomer, right, and that would lead to the really bad birth defects. So I will say it's a really good success case for the Food and Drug Administration in the U.S. Since then, this drug has been successfully shown to treat leprosy. It's also used as a chemotherapeutic agent for cancers. All right, so it does have some success, but obviously not met for pregnant women. So, all right, so serious consequences with chirality. Right, a lot of drugs you will see chiral centers on those drugs, and those chiral centers are specific to the activity of the drug, right? So you change the chiral center, not any of the composition, right? Just the configuration around the chiral center, you completely change the nature of the drug because basically the shape of the molecule changes, and now it can't fit into the same pocket it would have fit into otherwise, right? So all of these molecules you can see have R and S in front of them. This is just a way of naming molecules. So let's do. So whenever we treat this molecule, sodium borohydride, we're going to make two enantiomers, right? So you could just really quickly draw out those two enantiomers. Right, so these are the two enantiomers that you should have come up with. Okay, as long as you have these four things, right, the hydroxy group, the hydrogen, the ethyl group, and then this ethereal group, right, as long as you have those four things on the molecule, right, to draw the two enantiomers, you either switch the groups from the wedge or the dash. Right, so actually let me draw that down here. Right, so we could represent them like that, right? Or the other way to do it is, remember these are non-superimposable mirror images, so if we just draw the mirror image of this, right, that would also be a correct way of drawing the enantiomer. Okay, so these two here, these are just the same molecule. Okay, and then just flipped around like a pancake. Any questions? Okay, so communicating RNS is, actually, let me draw the other one. Communicating RNS is very similar to communicating E and Z in alkenes. And so what we have to do is we have to assign priority of groups around the tetrahedral center, just like we assign priority of groups around an alkene. Right? The difference is with alkenes we only have two groups, right, to judge higher and lower priority. Around this tetrahedral center we have four groups that we actually have to put in order from highest priority to lowest priority. All right, so remember priority is based on atomic number, right, or atomic weight. Right, the higher the atomic number, the higher the priority. Okay, so we will give in this molecule, or around this center, up here, you can see that that carbon is attached to an oxygen, a hydrogen, and two carbons. So which of those four substituents gets the highest priority? The oxygen, right? So we'll say oxygen is the first priority, right? And then is there a low priority atom that we can identify quickly? Yeah, hydrogen, good. So that would get a 4. Okay, and then you can see that we have two carbons. So remember, when we get here, we're not judging based on the size of the group, right? We're not judging based upon what group looks funnier, right, or better as a higher priority group, right? We're judging based upon the atomic number. So when we do this, we have to move out from the center atom by atom, right? So here you can see that the tetrahedral center is attached to two carbons. So at this point, we can't give a difference in priority. So the question that we have to ask ourselves is, what is the highest priority group on this carbon, and how does that compare to the highest priority group on that carbon? Right, so what's the highest priority group on this carbon? Highest priority atom? Oxygen. What about on this carbon? Carbon. So at that point, we can say oxygen is a higher priority atom, so the group to the left gets the higher priority of the 2. So that's going to be 2, and then that's going to be 3. Right, and we can apply those same numbers down here. Okay, so we've given groups priority. All right, now there are 3 different methods that we can use to assign RNS stereochemistry. Okay, and these are all methods that we use independent of one another, right? So we don't want to combine them. All right, the first is something to use if the low priority group is oriented backwards. Right? Then what you can do is look at the other groups, and if the other groups go at 1 to 2 to 3 in a clockwise fashion, right, then that is going to be an R center. If the other groups go 1 to 2 to 3 in a counterclockwise fashion, then that's going to be an S stereo center. Okay, so we'll go over this in a second. Okay, so this first method, you can see that one of the structures that we've drawn is drawn in a way that the lowest priority substituent is oriented away from us, right? Oriented backwards, or is the hash substituent, right? This is the only case where that's a hash substituent that you can use this method, right? If that low priority substituent is coming towards you, if it's in the plane of the paper or in the plane of the board, right, then you cannot use this method. Okay, but so on this molecule we can. So what we see, low priority substituent is oriented towards the back of the board, and if we order the other substituents 1 to 2, 2 to 3, right, what direction is that order going in? Counterclockwise, right? So this should be the S stereo center, right? Because this is the enantiomer, we can just say that this is going to be the R stereo center. Questions about that? Okay, so often when you see a molecule drawn on a page, it's not going to be drawn in a way where the low priority substituent is oriented backwards. Okay, where you can't use this first method. So we need another method for you to determine whether a stereo center is going to be R and S. All right, and this is the one that I almost always use. All right, I call this the hand method. Okay, and the way that the hand method works is you want to make your thumb, either on your right hand or your left hand, the low priority substituent, all right, and orient your thumb in the way that the low priority substituent is oriented, right? So we're going to take a look at this bottom molecule here. We know it's R already, but we'll prove that with this method. All right, so here our thumb is oriented towards us, right? Say, who's got 2 thumbs and is awesome at organic chemistry? That's right. You can say that at the end of this. All right, so a thumb is the low priority substituent, right? So I'm going to just choose one of my hands and say, okay, thumb, or the hydrogen is coming towards me. I'm going to point my thumb towards me. If my fingers curve in the direction of priority order 1 to 2 to 3 with my right hand, then it's going to be an R, right? If I do it with my left hand, right, then it's an S. Okay, if we look at this, my thumb's coming out in the direction of the hydrogen, and my right fingers curve from 1 to 2 to 3, right? So this has to be an R substituent. Yep.
So the 1, 2, 3 doesn't have to be in order, like it could be like.
It definitely has to be in order.
Well, but like the lowest priority is in between the 1 and 2. That's okay.
So it's not in. So remember, this is a tetrahedral center, right? So it's not really in between. Right, if one of them is coming out, then the other ones can be in order, right? If we take one out. So, and if I try this to do this with my left hand, right? Again, hydrogen's coming out, so my thumb's coming out. My left finger's curve from 1 to 3 to 2, right? So obviously it can't be an S stereo center because I can't do that same thing with my left hand. Okay, this method you can use, you know, in any direction, right? So we can apply this method to this molecule too. All we do is just stick our thumb away from us, right? And when we do that, we can see that my left hand, my fingers curve. If my thumb is away from me, right, my fingers are going to curve counterclockwise, just like the order of priority here. Okay, so this is a method that you can use no matter how that molecule is illustrated, right, no matter which orientation it's in. Okay, the third method, most foolproof. Use your model. Right, so just make a tetrahedral center. Doesn't have to be a full molecule, you just need 4 different colored atoms on that center, right? A white one, a black one, a green one, and a red one. Right? And you'll order those in alphabetical order, the same as you would priority. Right? You make an R center, you make an S center, you know which ones are which, right? You line them up with the molecule on the page. If the R center lines up with the molecule on the page, then it's an R center on the page. The S model lines up with the molecule on the page, then it's an S center on the page. All right? Model kits, I know some of you do not like them. I think they are great providers. All right, so those are the 3 methods. Again, you can't take parts of this and apply it to this, right? But these are the 3 methods that I've found to be most useful. All right, questions? We have 3 minutes left, so why don't we do a practice problem here? Actually, before we do practice, I do want to say one more thing. So, so we can also communicate the face that a group is adding to make a chiral center. Right? So these obviously are not chiral centers, but we know that if we add a nucleophile to this face, right, it's going to form a different isomer than if we add a nucleophile to this face. Right? So we can apply the same priority rules. So oxygen would get 1, this carbon would get 2, that carbon would get 3. Right? And you can see that we're going in clockwise or counterclockwise fashion. Opposite is true here. Right? And so we can, because this is going clockwise in order of priority, we would call this the psi face of the carbonyl. Right? And we would call this the V face of the carbonyl. Right? And we do this so we can say, okay, if I add a nucleophile to the psi face, a hydride nucleophile to the psi face, I'm going to make this specific enantiomer. Right? If I add a nucleophile to the reface, I'm going to make this specific enantiomer. Right? So it's a way to communicate facial selectivity on a carbon. Okay. So what I want you to do, we're not going to have time to go over this today because we're at the end of class, right? What I want you to do, copy this down, and then we'll go over this first thing on Monday. See if you can identify the chiral centers, right? And name the correct stereochemistry as either R or S. Questions today? Okay, great weekend, guys. You have physics exam next. Good luck.